In this video, we're going to go through the logic and an algorithm of sorts for deleting an item from the binary search tree. I think some of you are getting a little confused on what a binary search tree does and how to do this delete. So we're going to think about it. We're going to talk about it a little bit. Okay. So remember the binary search tree, everything to the left, the entire subtree. Okay. So for 30, everything over here that I'm circling, hope you can see me circle that. Everything over here is the left subtree. Everything over here is the right subtree. Everything in this left subtree is less than 30. Everything in the right of this subtree is greater than 30. Okay. That's true for every node along the way. Okay. So when we're deleting the easy cases, the easiest case is we have to delete something with no children. Okay. Let's say we want to delete 35. Okay. We would just delete it. Boop, it's gone. It has no side effect anywhere else. Okay. We don't really want it to go though. Okay. Um, the next case is if something has just one child. Okay. So let's say we've done that. Okay. And now we want to delete the 40, which only has one child. We would just move this 45 up to here. The 50 would go left to the 45, which is smaller than, and things are fine. Okay. So those are the cases there. But the complicated case, let's say we want to get rid of the 25. Okay. So the 25 has two children. And if we give the command or the function delete node or delete whatever you want to call it, if it takes 25 as its value, you first have to ask the question, is 25 even in the tree? Okay. And we have a function, hopefully you've written it already. The search function is a Boolean function that will find whether or not 25 exists or whatever exists. Okay. So I would start by saying, if not search 25, then say, can't delete it, doesn't exist in the tree, and return from the function because you're done. You can't delete something that's not there. Okay. But if you make it past that, if you're in the else for that one, or you wouldn't need an else since there's a return. But if you don't get caught by the if, then you know that the 25 is in the tree. Okay. So you have to get to it. So you'd have a pointer starting at the root, and you're looking for 25. Is this 25? It's not. Go left. Is this 25? It is. So now we're here. Okay. So this becomes whatever you want to call it. You could call it, we have to call it current, would be a pointer to a tree node. Okay. That's going to point to right there. And that is ugly. Let's see if it'll let me make that a little better. The text boxes are very strange. There we go. Looks better. Okay, so current, I don't know why current's two-sided, but you get the idea. Current points to here right now. Okay. So this is what's going to go away. We know it has two children because current left link is not equal to null and current right link is not equal to null. Okay, so we know we're in the worst case. Okay. So when we're looking for candidates for this, okay, it to fill in this, okay, it's got to be one of these from down here, right? It can't be any of the ones to the right. They're all bigger than 30 by definition. So that's not going to work. So it's going to be either the 15, the 27, the 5, the 20, the 26, and the 28. It's going to be one of those, okay? Further, we can eliminate anything with two children because if I would move the 15 up to here to replace it, like we would do if we only had one child, well, then 15 would have to point to the 5, the 20, and the 27. It can't do that. Okay. So we know we can't deal with anything except leaf nodes. Okay. So we'll go ahead and make these our candidate nodes. We've got this one. We've got this one. I'm picking a different green every time, which annoys my OCD, but such is life. Okay, let me go back here, get this one, this one, this one, and this one. Okay, these are all leaf nodes. Okay, so these can all be the correct. These could be. These are potential, at least structurally. Okay. I'll make the greens the same. I know it doesn't make much sense to you, but it makes me crazy. May make some of you crazy too. So anyway, okay. So these are the only potential ones that we have. Okay. Oh, sorry. Let me skip this last part. These can't be because they're on the wrong side of the tree. Get ahead of myself. Okay. This is why it's important that you draw a picture for these. If not, I think it's very hard to maintain what you're doing. Okay. So it's these four. These are the only candidates to replace the 25. Okay. Again, it can't be 35 because 35 is greater than 30. It'd be on the other side of the tree. Okay. So let's think about this one. What if I were to make 5 a replacement for this? Okay. 30 comes over to 5. That's fine. That's less than. But 5 goes less to 15. 15 is greater than 5. 5's not going to work. Okay. So 5 we have to eliminate for possibilities. Okay. What about the 20? If we have a 20 here, 30 goes to 20. That's less than 20. 15 is less. 5 is less. 27 is greater. That's good. That would work. 20 is a keeper. Okay. What about 27? We have 27 here. 30 is less than 27 or 26. Sorry. 30 is less than 26. 26, 15 is less than that. 5 is less than that. That's good. Okay. Uh, that all makes sense. Okay. So it's less than 27 or the 27 is greater than. So we're fine there. So that would work. Okay. 28. Okay. 30 to 28 is fine. But this 28 to 27 would not be okay. So that's not going to work. Okay. So we're left with 2 contenders to replace this. Okay. We're either going to replace it with the 20 or the 26. Those both work. Okay. And what we're looking at, if we had a bigger tree, we would find the same thing. We're looking at either the biggest of the left tree, left subtree of the current node, or the smallest of the right subtree. Either one are fine. Okay. We can pick either one you want. The book focuses on using this one, the right subtree. Okay. The smallest of the right subtree. Okay. So how are we going to find that? Okay. You can either do this in the delete code, or a lot of times there'll be a separate function you'll create that will just do this. It will take a node and it will find the smallest. Okay. So from we're starting at 27 here. So it's the left child we're talking about. From 27, how do you get to the smallest node? You keep going left, left until you hit a null. In this case, we just go left once. Okay. But if we were trying to find the smallest of the tree that started with 50, we go left and left to 35. Okay. So we're at 27, we go to 26. We can't go any further because of the null. So that is the value. Okay. So that's the smallest on the right subtree. Okay. So then to replace that, I think what I would do, and I haven't thought about all the ramifications of this, but this is just off the top of my head. If I save this value 26 somewhere, okay, then I can go ahead and get rid of this node. Okay. And then change the info of that node to 26. Okay. And then put it, now it's back to normal. Then you can get rid of the 26. Okay. So that is how you would get rid of the 25 and replace it with that. Okay. So again, we could go either way, but we're going to pick one. So we don't have to do two things. We're always going to know. So whenever we're deleting a node with 2 children, we're always going to find the smallest of the right hand subtree. Okay. So if I were going to delete the 50, I would go the tree starting at 60, the smallest is 55. That's what I would replace it with. If I'm going to replace the root, okay, I'm going to replace this with the smallest of the tree starting with 50, which is left, 35. Okay. So that's how we do that. So in your code, that's what you need to be doing. Okay. If you don't understand it, if you can't solve a particular problem on paper, then you can't solve a problem in general. Okay. So if you have questions, it's important you understand this. We're going to go into more with trees, using trees for programs, and we'll need to understand how they work in pretty good detail.